Hello, how's everybody doing? I hope you're doing good. So we're going to go over the last unit in this class. We made it. Let's check out Canvas. Will be assignment 12. We're going to go over today. So today is going to be the last lecture. We are going to go over unit 12 assignment. For next week, you are to work on your course project and there is a quiz. So I will turn on the quiz and a quiz review game so you can use the review game to access your quiz. And then, or prepare for your quiz, and then you will work on your course project. There is no more lab in this class, as you see. And this is going to be the last lecture that we're going to have. Now, on Monday and Thursday, I will be available between 6 and 7-ish in case you have questions, or if you want to make an appointment or show up on during my office hours, we can talk about your project if you wish. But I will be available in the evening to help if you have questions. I will not require any more assignment or lecture as far as coursework. You are to work on your course project, get all your components completed. Make sure that we are individually submitting our course project parts, even though you work in team. So make sure that you have all the parts submitted before it's due or by the time that it's due. You will also have a final review. Actually, I might have to do final review with you guys. So hold on 1 second. Let me take a look. I do have it pre-recorded, but what I can do is I can do final review where we go over the questions. Okay, so let's do that next week. On Tuesday, for both parts. You won't need to submit the final review. It's just going over the questions and be able to understand and remember some of the things we learned earlier in the semester. You will have a final exam that's going to be activated in June. So, and I will require lockdown browser. So you will see that I will send out notification via announcement for your final exam, final review. So we will go ahead and prepare for our final. And as we're coming close to the end, make sure that we have things completed. If you have any outstanding assignment, I need that in by the 28th of this month, which is you do have a couple weeks left. I know I'm behind on grading, but I will catch up tomorrow because there have been events and things that came up. So if you have things that you miss, make sure that you completed quiz, assignments, and anything like that. Okay. So for now, what we're going to do is we're going to go over recursion and data structure in C compared to LC-3, kind of give you a little bit more understanding on how you can implement some coding for your project. So in order to kind of dissect through the assignment, we will need to take a look at the unit notes. That we are going to cover chapter 17 and 19. And these are the two chapters that we're going to have to cover for the semester. This is the last part of the class. Okay. So in chapter 17, it mostly covers recursion. Recursive function is often used for a lot of different things. To be able to calculate sequence, sum, or aka series. You also see this in a lot of different type of algorithm. Now, as far as practice, in the field, sometimes you don't see recursive function being used too much because sometimes when we apply to a large data set, recursive function tends to be a little bit delay in performance when you're dealing with a very large data set compared to the smaller data set. But if you do research, programming, or if you do like study analysis and things like that on the smaller data sets, you would see that recursive function is often be preferred in mathematics because it is very clear and it is easy to write. So recursive function is a way that we can use the task by calling itself. So basically it is a function that continues to call itself. The example that you see here is a running sum. We often see running sum in a lot of our program, especially if for those students who are writing recursive functions to be able to calculate things that get added to the cards, or it is adding the same number repeatedly, so we can just have the function call itself. So in the mathematical definition, you would see something like this, or sometimes it's written like this, but we would have a running sum of 1 is 1, and the running sum of n is n plus the running sum of n minus 1. So it takes the result from the previous value, which is the sum from the previous number set, and be able to add it to the current number. So you would have a running sum. Now in C or C++, you would see that it is written like the box on the right-hand side. So you need to type your function just like all the other function. You would give it a name, and then you would use the parameter to pass the variable that you want to implement in your code block. And then for the recursive function, normally we have to state the condition of what n would be, where you want to begin. So we would say if n is 1, return 1, else we would return n plus running sum of n minus 1, which is the previous value to n. And so when it execute, we want to store that into a variable, and we want to pass the value for what int n would be. So in this case, we use 4. So it would take 4 as a parameter and then apply that to the function, store it into the res variable. So then we're able to return 4 plus the running sum of 3, which is the n minus 1. And then, so we would continue to do that. So what you see is every ladder that you see, we have returned. So in order to return 4, it has to return 3, and it has to return 2. So it has to compute. And this is often what you see with running sum or even series, where we would take the prior values and add it. And in order to generate the prior values, we have to have the function call itself. Now, in some cases, you do see employers asking you to write recursive function for interview or test before you interview. So make sure we understand how to do that, right? And for C, it is a strongly typed language. And when you look at the recursive function, you would see that it is calling itself to get the result. So it has to generate a return value from the prior number in order to add it to compute the current value. So what you also see is you would see recursive function being used for binary search, and this often come up for interview question, like to be able to write an algorithm for binary search. And for those of you who took discrete, you understand what binary search is, or if you took programming classes, they might have covered binary search. So in this example, we would have a set of exam score. And we want to, and for the exam, it's going to be sorted based on alphabetical order for the student name. And we want to find a certain exam score for a certain student. So now if you're only looking at the student, right, that's also a container. Compared to exam score, that's also another container. So if I'm only sorting through one container, for example, student name, right, I want to be able to search for a particular name. Now, in some algorithm, it's going to have it pre-sorted. And for binary, a pre-sort mechanism is going to be helpful. So that means that I have to start the container with an order, so an alphabetical order. So we're going to go from A to Z. And then from there, what we're going to do is we're going to take that container. Let's say I have 10 students. It's going to cut that container into half. So I would subdivide that array into two halves. One is going to contain 5 students, and another is going to contain the last 5 students in the array of 10. So that means that we have to identify where the half point would be. And so with that, what we will do is we would divide it again into half. So then it becomes a quarter, and then it's going to become an eighth, and so on. So as you divide the container into smaller pieces, what that will allow the function to do is to be able to seek in a smaller container and be able to grow outward. So when we subdivide it into halves where we can't anymore, which is going to become one single element in a container. So I have 10 divided to 2 of the 5s, and then divided again from the 5 into a container of 2 and a 3, and then on the left, and then a 2 and a 3 on the right, and then subdivided again into individual single element container. What that will do is going to be able to narrow it down and make my search a lot quicker. Instead of using a linear base of search, which is where we would loop through and try to match up the character of the name. So binary search is often implemented for quicker search, where it's going to cut the container into halves and half and half again until it reaches on a very low half where we would have a single element, and it's going to search from there. So it's a way that we can eliminate the search mechanism for the unnecessary element or the element that doesn't match the search. So when we look at this from an algorithm standpoint, right, we would say, let's say that we name our function find exam, and we want to pass the student name, the start and the end. Why is it important to do the start and the end? Is because we wanted to as an array is a sequential container, we want to say that the start, let's say I have a last name that start with an A, and an N, a last name that start with a T. And then from that, we're able to identify what the half point would be. So in an array of 10 elements, I would take the beginning and the end. It's going to combine that and divide that by 2. So it's going to create a midpoint. And with that, I'm able to implement the condition where we would say if the end is less than the start, right, we would say that it is not found. So therefore, if you look at this part, it is important, it is essential for binary that we have it pre-sorted, because if you don't have it pre-sorted, what will happen is it's going to take a lot longer and it won't work with the way that we create the algorithm. So in the else section or the else if, what you see is you would then start with the half point to be able to eliminate the names are not matching for your search key. So you would say student name is name of the exam at the half point. So what we will do is we will focus on the half that potentially would contain the element that we're seeking. And then if it's able to find on that half, it's going to give us an output saying that it found the exam. Otherwise, it's going to search for the other half. So it's going to call the function again and start with the half point minus 1. And then we have to implement another else where it's going to search the half point plus 1 to the end. So you really have to give it a mark on where it's going to seek. And through the condition that we state here, we're able to identify whether it's going to find it in the first half or the second half of our container. But instead of rewriting the same function in the same way, what we can do is we can have the function that's calling itself, where it's going to apply the same mechanism into separate half of the container. And then as we did Fibonacci in the past, you have seen how Fibonacci work, where we take the two prior numbers and we find the sum to generate the next value. So, and we just have to start with the seed where we begin. So whenever that you see a function that's written mathematically with f of n minus 1 or f of n plus f of n minus 1, for example, you would see that we can apply the recursive function as we return the value for the prior output in order to use that value for the next output. So in order to get the next f of n, I have to have the result from the two prior number. And so therefore I can reuse the function multiple times. So Fibonacci is a really good example for recursion. And so if you get an interview for Fibonacci, you can simply implement recursive function. You can implement linear loop-based mechanism, but you have to put your output into an array or a container and then sum it up. So ultimately, you also have to operate a running sum. So it is ideal if you implement recursive function. So this is how Fibonacci would look in C. I have a function called Fibonacci. I pass int n as my variable here. And then I want to specify my seed or where I begin. Because with Fibonacci, you can start with 1 and 1 or 0 and 1. So I would say if n is 0 or n is 1, and remember when we're using the OR operator, right, it just need to check either side. If any of the side is true, then it's going to return here. Compared to the and, it's going to have to be true on both sides. So for the if here, it's going to check if n is 0 or n is 1, it's going to return 1 because those are our beginning values or our seeds. Else, we're going to have the function that's calling itself. So in the body of that same function, we're going to have it call itself by using its name and then pass the value for n minus 1, which is the previous number, add it with the result of the number 2 places before that, so n minus 2. And so when we evaluate this on stack, if you take this into LC-3, we start out with the main, and in order to compute the fib of 3, what will happen is going to push the call, right, and the callee for Fibonacci of 3 onto the stack. So R6 is going to get updated with the last value that was pushed. And then again, we're going to push the prior result. So we have to call the function for the prior value. So it's going to push Fib2. And then R6 is going to update because now Fib2 comes in after Fib3. And then in order to find Fib2, you have to have Fib1. So you're going to push Fib1. So with that, what we see is in order to get the third value, we have to get output for the second, which requires the first. So the last one that gets stacked is going to be fib of 1. And so R6 is going to be the meter on which one, right? And we talked about how the activation records, it's going to add all the variables and the parameters onto this, the activation record, and that gets added to the stack. So that just means that it loads it into a certain section of memory. And so when the main call the function, so main calls fib of 3, which calls fib of 2, which calls fib of 1. And so this fib of 1 is going to get pop up first. Why? Because in order to calculate 3, it has to calculate 1, then 2, then 3. So we have to begin with fib of 1 for the output. Then it's going to pop that off. Once it already has this result, it's going to use it to calculate fib of 2. Then it's going to pop that off. I already have the result of fib of 2. Then it's going to use that for fib of 3. So fib of 3 is going to be the last one that gets popped off because it's the first one that comes in. So when you do recursive function, the order of that is the most recent is going to get stacked first, and it's going to get unstacked last. Okay. Any question? All right, so let's answer some questions from our assignment. For number 1, it asks you, what is a recursion? It is the method to solve problem where the solution depends on solutions to smaller instances of the same problem, requiring the functions to solve tasks by calling itself on smaller pieces of data. So when we summarize this, recursive function is a function that calls itself. So it is a way that we can reuse that function to solve the problem. And in order to solve the entire problem, it has to generate and execute the task for the subproblem. Okay, so for the final exam, we need to know what recursion is and how recursive function works. So some of the example that you see in the notes, and also if you look at the things that we've done in the past or the program that you have used recursive function for, if you took some programming courses, we just talked about Fibonacci. So sequence like Fibonacci or Lucas number is often implemented with recursive function. Factorial is another good example because you are multiplying the value, or you're outputting the result by using the prior output. So factorial is a good one. Running sum, we saw that at the beginning of our lecture. And then random number generator. And we did a lab with random generator. We talked about what is pseudo-random, right? What looks like random, but it's not truly random. But random generator normally requires a seed and how we implement the algorithm. So a lot of the random generator that you see uses recursive function. Now, when you have the nth value as a very large value, you would see that some compiler, it's going to have a hard time generating the output, and it might spit out a memory address. It is because it doesn't compute fast enough, or it can't retrieve it as it is overriding some of the memory location, right? It gets stacked and unstacked quickly, where it loses the actual value. It just knows the location where it placed the result. So some IDE or some compiler, it's going to actually spit out just the memory address. It would say, this is where I would place the result, but I don't have the result computed. So that is often a problem using recursive function if you have a very large nth value. So if I say f of n is f of n minus 1 plus f of n minus 2 for Fibonacci, and I want to find the 2010th number, and in some cases, right, depending on the system and the compiler, it might not spit out the value. It might just give me an address of where that value might be. So you have to keep that in mind. When you implement algorithm, you have to know the weakness of your algorithm, potential issues that you would come across with the algorithm. Recursive function is not a solution for everything, right? It is preferred in the researcher community, but by practice, sometimes it is not ideal when you're dealing with higher or larger number. Any question? Okay, so we talked about Fibonacci, what that will look like. And so we explain a little bit of this on how things get popped off. Now, when you look at the activation record, as we talked about that last week, right? We know the activation record is a way that it maintain what variables, what local variables, what parameters or what the variable that you're passing in on a certain section of memory. So your temp is going to be referred to your local variable. That's the variable that goes inside your function. And then we talked about the dynamic link last time and how does it know where to return and what value to return. So those things goes onto the activation record and then your arguments, right? That goes inside the parentheses of your function definition. So what that means is here you would see a note. It says that the compiler generates temporary variable to hold the result of the first Fibonacci call. All that is a memory section or address that it uses, right, to hold the result. As I told you earlier, that what happens when it comes across the nth value that is a very large, it's going to give you this temp address instead of an actual value, because what happened is it's not able to compute or store a permanent value where it could retrieve to generate the later value. So you often see that problem where it would give you the temporary address of where that result might be. Okay. So in LC-3, we looked at this before. We wrote it a little bit different with Fibonacci. Now, when you implement stack with Fibonacci, what you would see is you need to use register 6 to be able to maintain what's here. So when we take a look at the activation record this way, so R6 is our meter on what's on stack and what's not, right? What's the top of the stack? So R6 is going to gauge like which one is on top. So that means that I have to start with R6 for my subroutine. And what we want is we want to push the return address. Why? Because that return address is where it's going to pick up back up for the program again. Now, keep in mind that this is only a snippet of what the entire Fibonacci program would be. So we're only looking at the mechanism on how it's going to push certain thing as part of the activation record. So here we're going to add -2 to register 6, and we're going to put it on register 6 again. So that means that it is going to go 2 slots down So you're subtracting 2 here is because if we start with the temp variable here, right, R6 needs to gauge where that return address is. So you're going to subtract 2 to go 2 down to the return address section. And then what we're going to do is we're going to take what's in R6 and we're going to store that out to register 7. Why register 7 here is because it's going to use this for the return value. Okay, so add 0, store it from R6 to R7. Then we have to push the dynamic link. So now R6 is going to move 1 down. So if you look at this, right, so we have it here. So what we're going to do is we're going to move 1 down. So that's going to gauge at the dynamic link. This is going to be the address or the location where it's going to be. So you're going to subtract 1 here. So we're going to push the dynamic link. So whenever you push, think of it growing downward like what we've been talking about. So that means that we have to subtract the 2 location to start for the R6 and then the 1 location for dynamic link because R6 is at where your temp begins. And then we're going to store that again to register 5. Now R5 was in the last chapter, we talked about how R5 is being treated as the pointer, right, for your frame or ultimately your activation record. So you need to store it out to the register that's going to be in charge of that. And then once again, we're going to add -1 to R6 and put it on R5. So coming back here, right, we are here with the -1. And then we need to add the -1. So that way it can look at your local variable and eventually your arguments. Okay. So once we have the frame pointer, now we're moving down to 1. And so it's at the location for the pointer. Then we're going to subtract 2. That's going to allow us to access the locals and the temp. So that's going to be the temp here because as we subtract 1, we bring it back to the temp. And then we have to subtract 2 from the dynamic link to go to the end. So you have to visualize it. It is very physical in the way that the abstract way that we think about where we go from the top to the next one and then back to 1 and then back to another 1 and then down to 2. So that's going to get you to the return value. So here is where we were able to access the locals and the temp. And then in order to now at this point, it's going to say, okay, now I see your n is your variable for parameter, right? Or what you're passing. At that point, what you're going to do is you're going to then load your value. So now we are going to pass the value. So 4, right? Because we talked about fib of 4. And that's we're going to load that to register 5. Why register 5? Because it is the pointer, right, to your locals and your parameter. And then we want to put that on register 0. And we want to branch for 0. So as long as it is not 0, then, when it's 0, then it's going to go to fib base, which we later define. So it's going to check for the exit of the loop. Okay. So ultimately your subroutine in LC3 requires, right, if we implement the stack and the way that we use the stack, right, we want to be able to implement pointer. We want to be able to implement the stack, the top of the stack, what is on top of the stack, and how it uses the activation record with the stack. But we have to find a way for it to either continuously doing it as it's stacking and unstacking, or it would need to exit and go to the next section. So here, fib base is going to be the terminal case. So if it branches 0, it's going to send it to fib base. then since our register 0 is loaded with the parameter, right, you want to add the -1. Why am I adding the -1 here? Sorry, I lost my little visualize. Okay, so we're back to the local and the arguments here because we just load 4 to here, right? And it's able to do that. So now we're going to subtract 1 again. So from here, it's going to bring you to the return value from the end. So then what we're going to do is we're going to push n-1. So when you add this, and you're going to push the -1 here. So that's going to allow you to see that this is n and n-1. So the location for n and then the n-1. And then we store that to register 0. And it is calling itself. So you have to jump to subroutine Fibonacci again, right? You call itself. Then after that, we're going to pop. So as we subtract from the top, right, we're going to add the positive. Okay, so as we add the negative on the top, now we're going to add the positive. So we are going to pop the return value, which is from register 0, right? We store that earlier. We're going to add the 1. We're going to move it back down or back up, right? I'm sorry, back up because we talked about how stack growing down. Then we're going to store the temp. Okay, read the parameter. So earlier you load 4 here to register 5. You got to reload it again as that needs to be applied for the pop. Now, what we have to say what n is. So we already have n for the n-1, and then this is n for the n-2. Then we push it again. So when you push, you subtract 1 here. So add the -1. And then when you pop, you add the +1. And then we store. So after that, we're going to jump to subroutine again because it's going to call itself. So what this does is breaks it into 2 sections. One part of the equation is f of n-1. So this is it. And you have to call the function because you have to operate what f of n-1 is. The second part is f of n-2, right? And so we have to call the function again. But we have to say what n is and what is the -2. Okay. So this is how you can implement recursive function for Fibonacci in the case that we have to call it twice in the same function itself. Right? Okay, any question? Okay, so that kind of give us a little bit detail on how that's applied to LC3, but on the high level, we can describe how recursion can be incorporated in programming, what happens on the stack, and what is contained inside the activation record. And this is kind of reviewing what we talked about last week. But to really summarize what we just talked about, when your function is invoked, right, your activation record is pushed on stack. We established that last week. But in this week, what you saw is that we gave it a value of 4. You want to find fib 4. So once the value is returned from the first call, so in order to find fib of 4, it has to find the result for fib of 1 and fib of 2 and fib of 3. So it needs to have the return for the first call. And it's going to take that and apply it for the next function call. So the result from the first call gets applied to the next call for the function, which is fib of 2. When it does that, it's going to update the activation record because now, right, the value that's returned gets added back into the activation record. So because this is the way that we do the bookkeeping of the parameter and the local variables. So Once it updates the activation record, then it's going to push it for the next call. And it's going to continue to do that as it is calling itself. So after the next call takes place, the activation record is updated again, and then it's popping off the stack. Because it has to pop off what was previously called that's already been updated. So this is why your stack grows and shrinks, not just because it's one function after another, but it is a function that repeatedly calling itself. So once it has the return, right, it's going to push the next call. Then it's going to pop, it's going to update the activation record. It's going to pop off the stack the previous call. Okay. Any question? All right, so we talked about what's happening with the function and recursive function and with the activation record and the stack. And this section on page 6 kind of show you how things get popped off, right? When it read the temp. We already have fib NF1 and fib NF2. So to combine that, you need to make sure that you add them together, right? One from register 0, one from register 1. But when it read the temp, you have to think about like how where R6 is and where R5 is. So your R5 is going to be your pointer. Your R6, it got to move back up because we had it gauged down earlier to be able to go to the location for the dynamic link or the variables and temps and so on. So we're going to add it back up, and then you're going to subtract 1 from, or you're going to load -1 from for register 5 and put it on register 1, which allow you to use that as Fibonacci of n-2. And then we're going to add that with n-1, which is for 0. And we want to branch -0 and positive. Now, I don't always like using all the flag like this. I don't want to use all of the bits set like this, because ultimately it is a BR when you're doing -0 and positive, because anyway, it's going to check true for here and it's going to force it to go to N. So you can do an unconditional branch. So the way that they did this is whether it's negative, it's going to go to fib N. Whether it's 0, it's going to go to fib N. And whether it's positive, it's going to go to fib N. So it is exactly like if you're using unconditional branching. But when you apply all the 3 conditions like this, any of the condition is going to force it to go to fib N. Okay, so when it's done, you want to send it over here to pop. Okay. So it shows you in each line on how it pops the dynamic link. And then the return address. So anytime that you deal with return value and return address, you want to bring in register 7. You want to load that. And then you got to grow it back up. So you got to add 1 to register 6. Okay. Any question? Okay. So that takes care of number 3. Then we're going to move on to the last chapter of our text, which is going to be 19. And this is the intention of this particular chapter in this section of the lecture is to kind of sum up what data structure would be and how that is equivalent to LC3. It is not intention. The intention is not to really explain to you the entire course of data structure, as some of you already took 17C or currently are in it or will be taking data structure. Data structure is, it entails a lot of different components, right? But we want to have a general understanding of how to really apply data structure in any form of programming. I think it's really important that you think about data structure when you write your program, whether it's in LC-3, C++, Java, Python, JavaScript, whatever, right? You need to really think about where your data is contained and how you can improve performance by accessing your data a certain way. So to really define data structure, it is a way that we organize data on memory. So it is an organization of data in memory. And we want to group together the related data or similar data, right? The type of data that is the same. So we want to group them together. So that way we can achieve efficiency. And so when we say efficiency, it's driven by performance. And ultimately, software is about where you place the data and how fast you can access that data, right? There are many different ways to write a program, but when you think about programming, you really have to think about how your data is, the placement of your data, and how you can quickly either group them together or be able to use your data throughout your program. And so at one point or another, either you're going to write or read the data. Okay. So when we use data structure, what we do is a lot of the times we group them together because they are similar or they're related. And that allows us to have convenience and efficiency. Now, when you look at different type of data structure, you might think about, oh, well, is it better to implement a certain type of container compared to another container? But you have to think about what is the purpose or the objective of your program? What is the intention for that data structure, that container? Okay. So a lot of the beginner student, they just use array. But if you think about C++, right? All the other container relies on an array. An array expanded how we access the array. If we're looking at linked list, doubly linked list, a queue, a deck, right? Ultimately, it starts with an array, but how we access certain part of an array at the beginning, the end, or both ends, is gonna give us convenience and efficiency. It's kind of like if you have a very long line of people. A regular array would be that you would accept one person at a time, depending on how they line up, right? Like from the beginning to the end of the line. But in some container, we're looking at doubly linked lists where we would take that line and we would loop it, right? The beginning and the end meets each other. And we can pull out different people from the line. Or what we can do is we can access it from both sides, the beginning and the end of the line. We can, let's say, give them tickets on both ends. So that way we can shorten the line quicker. So it's really a way that we can access data on memory. So you can find this information on your notes starting with page 6. And this is where you would look at the bullets. That's how you're able to put together the answer for that question. So some of the example for C for data structure, you probably heard of struct. This is directly supported by C. And you see that also in C++. You can have a linked list or a doubly linked list. It is a way that we can take a struct and we can use dynamic allocation for memory. Like what we can say, we can take the beginning of the line and the back of the line, we can link them together. So the cool thing about the struct is that you can group different types of data together. So as you know that C++ and C is a strongly typed language. We can either have an int, a double, char, possibly we might have float, right? But what if I have a combination of data types? What I can do is I can create a type that group up different data types by using struct. So in this example, we're building a program for aircraft. So you might have char for character for your flight number, as many of you have been on a plane before or seen how flight system works. We might have altitude for int, longitude for int, data type int, and so on. And then the heading might be int, the speed might be double. And we don't want to manually handle these type individually. What we can do is we can create a struct like this. So you can say struct, give it a name, open your curly brace, and then inside the body of that struct, you would list the member variable. Okay. So when we look at the allocation in memory, right, recall that this is your struct is your flight number. It's going to allocate your member variable based on, right, how you define it here, of course. Because for your flight number, as it is char, right, 1 character per word or per memory address. So you have 7 here, so that's an array. So it's going to cut up the array for that one first. 0 to 7 right there, right? And then after that, we would have the altitude, the longitude, the latitude, and so on. But remember that now these are part of the struct. So this is a way that we can conveniently group them together, even though they have different data types. Any question? Okay, so some of the important things to note here, it says that to allocate memory in a struct, we declare the variable using a new data type. So when you say struct here, right, you really create a container that encompasses different data type where it grouped them together. And the memory is allocated and we can access individual member for this particular container. So ultimately, it treats it like a container that has different variables within it. But all it is that it put them together in one section. Okay, so you can access it quicker instead of just dynamically allocating them across different areas. So for number 5, we can say that a struct is a mechanism of grouping related data items of different type in C and C++ programming. Some of you have learned this in CIS11 or 17A or sometimes in 17C. And you can use the one in the notes for number 6 as example, but what we can do is we can say, okay, I can create a struct called food, right? And similar to class, you want to capitalize the name of your struct or the identifier of it. And for the member variables inside here, you would follow that and put it inside the curly brace. And here we need to type them. So for my food, let's say I want to write an application in C or C++ that calculate, right? Maybe food price by weight or whatever it is. So I might have a member variable called weight, and its type is double, because you might have 17.26 pounds, right? So we want to use double. And then for price, we can also use double. Like my price can be $2.99. And then my description for the type of food that I'm selling, and it could be online, right? It would be string. So I can have like black beans, long grain rice, etc. And then in some cases, our food would have size, right? Like you might have a large bag of beans that's weighted 50 pounds, small bag of beans that weighs 10 pounds. So size. And we can go on and add more variables, of course, but this is just simply an example to show you that we do have different types here, right? But can you use the same? You can. But the whole point in having a struct is to be able to combine different types into one structure, which you create a new type called food. So it's going to access this by saying food.weight, food.price, food.description, food.size. Because now this belongs to the property of food. Any question? Okay, so that's one example, and you're welcome to come up with your own example. I'm sure some of you have written program with structure. Let me bring this down a little bit so in case you're still recording number 6. So for 7, it asks you to describe how memory is allocated for a struct. So memory is always allocating dynamically as needed. And what it does is we don't really group things together sequentially, right? Like the picture that you just saw, we're trying to make you visualize that, yeah, it's supposed to be together. But in memory, it's going to be wherever that it can find. But how we can structure it on an abstract level and make it look like it's together is to use pointer. So ultimately, when you're writing a struct, it's going to point to the container that are grouped together. Okay, it's not physically actually together. It is dynamically. So I might have different areas, but what it does is going to point to them as they are together. Okay, so I would have weight, after that price, description, size. So So it uses pointer to implement contiguous memory allocation of the members in the struct. Because if we would take all of this and then move them to be in the same area, it would take a long time. So a way that we can bypass that, if you're looking at hardware level, what it does is it's really using a way to point it so that way they are near each other or next to each other. Okay, instead of moving them to be contiguous. Any question? Okay. So some syntax information is here, right? You do see some examples. So this gives you a little bit of illustration on how it's accessing the array, which is the char, and then the other member variable as we create a new type like plane. So on the LC-3, and again, right, they only show you the snippet of this right here. So what we're going to do is we're going to clear out a register. And what we have to do is we have to create, right, what seems to be a contiguous memory allocation for all of the member variable. So you got to think about, is there an array? How many member variables are within that struct? And I understand that the compiler handle all of this for C and C++, right? But on the low level, you take the register, you clear it out, and then because R5 is going to be our activation record register, why is it subtracting 13 is because we are growing downward in the memory. So we have to allocate 13 section for the member variables within that struct. Why 13? Why not just the member variable, right? 13 is because you have these as variable and the first part is the array. And for the char, it's going to require 1 per character. So as we have 7, right? So we have to have 7 here plus 6 variable. That gives you 13. So therefore we have to cut 13 for the struct. So this is why you see it subtracting 13 here. And we want to place where that array is, right? Because that's going to give us the next variable here. So for the 8th word, which is the end of the array, that's going to be your next variable after the char flight number, which is altitude. Okay. So what it does here is we have to store 7 to register 0 as register 0 and store, right, where at the end of your array for that, and then be able to start with your member variable. Okay, so this kind of show you how we can cut out the array inside that struct and then place the next, store the next part. So that's going to be the mark where the next, your next member variable would be in the struct. Now in the next section, it talks about what if it's an array of structs, right? You can define it as an array, but as you do that in C, C requires that you specify the length. So And then you would use the index value to access specific element, same like how you treat a regular array. So you can make a struct not as a variable, but as an array. If you use it as an array, you simply use the square bracket and then put in the length of that array. Okay. And so what you would see is that we can use it as a container or a way to group many things together. And then you can also use pointer as struct. So let's work on the next part here. So for question 8, it says, in an array of structs, how does the member access? We simply would use the struct name and separate it with a dot operator. And then we would use the index value. So it would look something like this, plain dot. Oops. Let's say latitude. Any question? And then we can pass it as an argument. We can also use it as a pointer. So for a struct to be passed as an argument in C, we want to use it by value into a function. So when that happens, the members inside the struct are going to be added to the activation record as they are variables or container, but it's not copied. Okay. Because in cases where we would see that it creates a copy of those variable, but in this case, what you see is the activation record actually have the members. It is not a copy of the members. So we talked about that here, right? Oh, I had written this backwards. So let's see. Should be 4. Sorry, long day. A little tired. Okay. Then for this part, if you wanted to read more on passing the struct as arguments, right? We say that it's always passes a value into a function. The struct members are copied into the activation record, and changes inside the function does not reflect the routines. So when you're passing into this, it's what we will see is that it's copied into the function's activation record. But when you pass it as a value, it doesn't do a copy. Okay. Now for the pointer, you can also pass the pointer, like this one you see, plain A, right? Plain B. So when we look at dynamic allocation of memory, what we have to think about is that array cannot be dynamically allocated. because they need all the indices or all the elements, they need to be contiguous. So when you treat struct as an array, you have to think about how it's pointing that as a contiguous space. So it's using a pointer and pointing it as contiguous space. We must know the number of elements that it requires in order for the low level of the compiler to cut up how many memory locations that it requires for that struct. So that means that we have to know the length of your struct array. Otherwise, we would end up wasting space, and then it would affect the performance of your application. So here what you see is that we need to think about how your storage is dynamically allocated. That means that it's going to put in wherever that it can find as needed. Okay. Now, if you're looking at your STL, your C standard library, right? Some of you might come across like malloc, and I address this in my CIS11 class. Malloc is a way that we can allocate and use a generic pointer to section the memory to specific size for the container. So what it does is going to cut up the bytes that it's needed for that region of the memory, and then that's going to lead us to the heap. So for C, when you often see the void malloc like this, it is the way that we can handle dynamic memory allocation. MLOC stands for memory allocation. Okay. And then you would pass the number of bytes. So let's say that I need 4 bytes. That gives me 32 bits, right? That's going to be the value that passes in here. Okay. So using some of the STL, you would see that you will be able to use the function to be able to cut up certain section or a certain amount of memory that you need for allocation. And so that leads us to heap. And we spent a lot of time talking about stack, right? And we know that stack is rewritable but not executable because stack can change, but it's not executing here. The compiler handled this. Then you got dynamic data, which is heap. Okay. This is, you think of this as user data. So this grows upward, stack grows downward. And heap is writable. It's not executable like stack. But stack is handled by the compiler at low level. Heap is handled by the programmer. Then you got static data, which is not executable and writable like the others. This is where it begins. So initialize when the process starts. Then you got the literals, which are what you normally see as variable assignments or assigned values, right? When you initialize, like you can say int n is 5, right? Those are the literals. That's also used when it starts. Now, when you write LC3 instructions, right, like add, and, load, that is going to go into the instruction sections. It's also, so all of these are required for it to see, right, what kind of data, what's the value for the data, how it's going to handle the data on the low level. And so ultimately, it's a way that we use memory to be able to execute things by either accessing the data, right, point to the data, and group the data for our program. So a heap are bytes that are allocated in a certain region of memory, and remember that heap grows upward. And often you would hear this as dynamic data or user data. This is handled by the programmer. So for number 10, we can say that memory location that is writable and not executable, allocated for data type, and it is managed by the developer. And heap grows upward. Stack grows downward. And of course, they always have a ceiling. So there's a certain amount of memory that's allocated. Of course, it's not infinite. Okay. So earlier, I mentioned about malloc, right? How you can use malloc in C. You would be able to set up the certain amount of bytes that's allocated. It's really depend on how you want to handle the storage for the data types inside that struct flight. And it does do casting, so it would size up or size down depending on the type that you work with. Okay, so when you change the type, what that does is going to use the pointer to properly cast. It really depending on the type, right? Like when we talked about casting, it just means that like when we can go from inch to double, where we can go to from small to large, or sometimes we size it down, or sometimes by rule it just casts it down. So from a larger size to a smaller size, but a lot of the time we cast it for the larger container. So when we're looking at the heap, we already talked about the stack. Things get popped off, right? One's like if you're looking at the function of the subroutine. But for the heap, when the data is no longer needed, right, it gets off of the heap. So it's being released back to the heap for the later use. So it does give back that space, right, for other use. And in C, when you look at C, the way that they do this is to be able to use a free function, or what we see as a way that it free up the memory. Okay, so when you read the malloc standard library, inside that you would see that there's the function called free. And what that does is going to return the space back for other use. Okay. Any question? Okay. One of the things that you want to notice that it says that if allocated data is not free, the program might run out of heap memory. So you would reach a ceiling and it's not able to continue. So you're going to have halt or error issues here, right? And you don't want that to happen. Normally, your OS is going to give you that memory address error, right? You're going to get a little pop-up message error, and then your program will not respond. So in the case where programmer create a program that doesn't free up the user data side or the heap side, you're going to have a halt program or a non-responsive program, and eventually it generates a memory error. notification from the OS side. Okay. So we want to be able to control the heap and manage the stack properly. Think about like what's on stack and how you use your function and how things get pop on and off, especially for LC-3. Next, we're going to talk about linked lists. I mentioned this earlier. So when I teach 17C, we spend a majority of the time working with, different data structure. Linked list is one of them. Now, linked list is particular to C, C++, right? Python in general, they just use like, the collection library, and you should use dictionary overall if you want to deal with larger container. But for C, C++, linked list is a way that we can use order collection nodes. And we want to put data, like I can have data in node 1, node 0, node 1, node 2. And we can connect them together. So simply I'm taking node 0 and then I have data here and then I point to the next node. So think of it like a train. You have the first part of the train that's linked to the next part of the train that's linked to the next part of the train. And at the end of the train, it's going to point to a node. Okay. And this is a singly linked list where it's going to go linear. One node to the next, to the next, to the next. Now, what if I delete data here? I can delete, right? But if I delete node 1, I'm going to lose the link. So I got to really be careful with which node I remove. So it gives you the characteristic of linked list or a singly linked list. Each node points to the next on the list. The first node in the list is called the head, which is we see here in this picture as node 0. And the last node on the list is called the tail. So node 2. And this can be many nodes, right? I can have 50 nodes in a singly linked list. So the last one, that's going to be the tail. That's going to point to the node. Now on the doubly linked list, unlike this, right? At the end, it's going to point back to the beginning. Okay, that's a doubly linked list where the end point back to the beginning. A singly linked list, it's just linear. So the head to the tail. So linked list, the way it's shown here is a singly linked list is sequential. Okay. So in order to access this node, I have to access node 0, then go to node 1, and then to the next one. So you must start with the head and link it to the later nodes. Now the advantage of this is I can add more nodes as needed. It is dynamic in size, so it can shrink and grow. We can remove nodes somewhere in the middle, right? So in the case where I don't need the data there, I can remove it. I just gotta relink it otherwise, right? So you have to redirect the link. That's very important. So if I add in more here, I gotta redirect the link. Otherwise, it doesn't work. So think of like the train, right? If you want to add another, then you got to reconnect it. Otherwise, it would not be able to move sequentially. So this illustration right here, right? I remove the link from node 1 and 2. I add in the new node. So you splice it. And then you add in, so you have to link node 1 to the new node and the new node to the node 2. Okay, and then when you delete, of course, we have to update the link. So when I remove node 1, then I gotta link node 0 to node 2. And keep in mind that this is an abstract way of thinking about how we're pointing to container that points to the next container and so on. Okay. But for the linked list, we identify which one is the first and which one is the last for the singly linked list. So when do you really see this being implemented? It can be in a lot of different types of program. For those of you who wrote trees, and there are different types of trees, right? You often see that a lot of these type of data structure gets implemented. Also hash table, there's so many other programs that uses this. But as you proceed to your higher level classes, the expectation from your university professor would be that you understand data structure where you would implement that into your program and not just using array. Okay. So for 11, we can define a linked list as an ordered collection of nodes, each of which contains some data connected using pointer. And we talked about the head and the tail, how the head is going to link to the next one. That's going to be the beginning of your list is the head. And then the end is going to be linked to the node, which is your tail. Whenever that you remove or add a node, you got to relink the nodes before and after it. Now, if we compare the linked list to the array of the data structure, your linked list is dynamic. It can shrink and grow. A singly linked list is accessed sequentially. You're going to go from node 0 to the next node. So if I need to access node 5, I have to start with node 0 and go down to node 5. You can easily add or remove nodes. You just got to relink them. They will relink the before and after. Now compare that to array of struct. What you would see is that you can access the element in the array of struct easily by using indices, right? We talked about that earlier. Because it is an array, it is dependent on the size, which is, the length of the array is the number of elements in that array. And normally when we handle this container, it is iteration. So that means that we sequentially loop through. Yeah. Okay. Yep. Good night. So when you're looking at the array as a container, in order to access the entire array, I got to start with the first element, loop to the next and the next and the next and the next. So in the struct that is treated as an array, what you have to do is you have to be able to access each element through a loop, or you can access it one single element using the index. Same concept as a regular array. Okay. So that means that the array is not dynamic, right? But you guys learn about dynamic array where you can make it, but ultimately it is size dependent. Okay, the number of elements really determine the size of your array. And at the low level, that it cuts up each index is each memory location. So if you have 7 elements, it's going to have 7 locations for that array contiguously. Any question? Okay, yeah, number 3. Are we good with 11 or 12 before I scroll back up? There you go. Yep, you're welcome. Okay. So as some of you are finished, you can add your name into the chat. I will stop recording so that way if you have questions or concern,